So first of all, thank you all of you to join this webinar on the motor NVH, like electric vehicle NVH. So, first I would introduce myself, Vicky Quad from ARK Infosolutions, and I am taking care of the low frequency department of the ANSYS. So okay, so in ANSYS, the whatever the applications that we are covering, whatever the simulations that we are doing using the ANSYS tools, which are comes in the low frequency domains, or you can say in the electrical applications, you can say shortly. Okay, so today's topic is the motor NVH, and we are first doing one presentation on the NVH, what is NVH and how it is happening, and how you can do the simulation of NVH. Okay, so it is very needful for the when you are designing any electric motor or any motor for any other applications like automotive applications or industrial blowers application, pump application. So that times sometimes you feel the noise as well as you heard feel the vibrations or harshness. Okay, so to get the best performance of the motor, we have to do the NVH simulations, and we have to minimize the noise, whatever the noise generated by the electric motor. We have to reduce that noise, right? Okay, so first I would introduce what is ANSYS and what are the capabilities of ANSYS, and then we will start our agenda. Okay, so first of all, ANSYS is the number one in simulation tools. Okay, so like the globally is around 7,000 employees are there. Here the 6,000 full time. This is the data according to 2022, and here you can see the proven revenue is there, like 2.7 billion US revenue is there, and from this revenue around 22 to 23% goes in the R&D sections to update the solvers, to update the whatever the simulations are there, whatever the updates are there. You can see in the in each year the ANSYS provides the two updates, so better understanding of the physics, better accuracy. You get the better accuracy as if you are using the updated version. And the main part is like ANSYS focus on only on the simulations. ANSYS is only on the simulations, not in the any other department. Okay, and the customer satisfaction rate, you can say, which tells us about the technical supports, how successfully you provide the technical support, so that the customer retention rate around 93%. Okay, and this is the ANSYS portfolio. So in the simulation industry, whatever the products that you have, whatever the products that you want to simulate, like before the prototyping, like in the product design stage, what you are doing, first doing the calculations, then we are optimize one of the product, and then we are going for the prototyping test. So okay, before prototyping we have to optimize that product. So if you are directly going the prototyping rather than the simulations, then the cost is very much necessary. The cost will be more when you are directly doing the prototyping. So before prototyping you have to do the simulations. So like today's topic is the NVH topics. So here you can see the product portfolio. ANSYS provides the product portfolio on any industry, like autonomous vehicle simulations. You have the materials for the material study. The Granta material is there, and in the electronic section the two physics are there: the high frequency and low frequency. So high frequency is for the in terms of the RF, like antenna design, 5G analysis, PCB, and for the low frequency domain the Maxwell tool is there and the Motor-CAD tool is there. Next the semiconductor is the structural physics, fluid, and these are the multiple technologies are there. Okay, next the cloud is there, mission engineering, the STK tool is there. So STK tool is basically for the satellite communications, then the optics if you are interested in the light phenomena, and the embedded software is also there, and the trending one is the digital twin builder is also there for the system simulation. So like if you have one of the electric vehicles and you want to do the simulation of that electric vehicles, so that you can do your whole system simulation. It is not like the only one part, because in electric vehicles only motor is not there. There is a power converter is there, right? There is the some mechanical components are there, gearboxes are there. So you have to combine all those components and you have to build the electric vehicle. Now you have to simulate that whole electric vehicle. It is not the one part only. We have to simulate the whole system. So that whole system simulations you can do in the twin builder. Next, these are the companies which leveraging our ANSYS platforms for their research and development. So like here, in every industry the industries are there, and these are the academic customers are there in India. Like it includes where IITs and NITs also. Now our today's outline is introduction to motor NVH, and we will do the ANSYS Motor-CAD for early stage NVH analysis. First we see what is Motor-CAD and what are the capabilities of Motor-CAD. Then we will see in the hands-on demo like how to do the NVH analysis inside the Motor-CAD. Okay. So now the first question is, what does NVH means? Okay. So for NVH is like noise, vibration and harshness. So noise is like in air, whatever the sound you hear in air. Okay, so that's called the vibration is there. So whatever the vibration, noise is because of the vibrations. Okay, but in air you can hear the noise, but in vibrations sometimes you see, for example in motors, okay, you are seeing for some disturbing parts are there, some vibrations are there, so that's called the vibration is there. Next, the harshness is there. It is like the human perception. Harshness is the human perception. So sometimes what happens, let's we compare the two motors. Okay, so one motor is like this, the sound frequency of two motors are same. Okay, but one feels, when you touch that motor, one feels smooth and one feels rough. So that feelness is there, and you can say the perception is the human perception. So that's called the harshness. So whenever you feel rough, so that times you call it as a more harsh motor is there. Okay, so that's called the harshness is there, and that is the actual meaning of that NV and H, noise, vibration and harshness. And now what are the challenges that we face during the NVH? First we will see the automotive NVH. Now in the automotive, what are the main noise sources are there? Because of the electromagnetics, some of the mechanicals, or some of the aeroacoustics, right? So first we see the electromagnetic. In electromagnetic, the motor design is there because of the stator imbalance. Okay, so that's causes the noise in the motors, or sometimes then the magnetic imbalance. Okay, then the inverter switching noise is there if you are using the PWM control or any feedback control system, like, so that time you feel some you get some noise in the inverter also. Then the mechanical noise is there, so due to the mechanicals you feel the vibrations also there because of the rotating parts which are included in the gearbox. The gears are there, the minute gears also there, different types of gears, the bearings are there, and the road noise also, and then a type of mechanical load variations also. And then the aeroacoustics noise is also there because of the wind noise, fan, pump, because of the water also, the flow noise. Okay, and one of the many requirements is there, the system performance. So we have to simulate the overall torque and power. Okay, then the efficiency and fuel economy we have to simulate on the various operating points. It is not like if you are running our motor on the running for one application, so it is not like you have to simulate for the only one condition is there. So you have to check the same motor on the different parameter, like it is whether it is working or not in the different applications. Like in the packaging sector, durability and NVH is there, vibration and acoustics. And next is the cost. So what is there? Poor quality of NVH means if your NVH is poor, then your quality of product is also poor. So that's why it is important to see how the natural frequencies are there, how the vibrations patterns are there, at which mode the how the vibration looks like. So that part we have to see here. Now in which applications you can see this NVH part, like in traction drivetrain, pumps, fans, that you already see, and these are the different types of machines are there in which you can see the NVH, the noise and vibrations. Now in ANSYS, what is the procedure of that machine design, like from scratch to the advanced level machine design to the manufacturing, how you can do that calculation. First we have to do the electromagnetic analysis, then we have to check the thermal performance. After the thermal performance, in the mechanical sections we have to see the durability test. Okay, the rough and tough, you can say, like the how much the rough and tough your motor is there, and for that you have to check the noise performance, noise and vibration performance also. Okay, then the operational performance making, you have to check the performance, like you are building one of the electric machine for the electric vehicle application, so that electric vehicle must be capable to do the performance of that electric vehicle. Okay, it is not like it is using the pump and they are giving their application. So it is not like that. You are using your electric vehicle, electric machines in the electric vehicles, like on the highway applications, like sometimes in the off-road applications also. And after the performance mapping, then the system integration is there, because in the electric vehicles only one part is not there. Along with the motors, inverters are there, mechanical parts also there. Okay, you have to check the reliability of the other components also. So that system integration you can do inside the twin builder is there. So it is a dedicated tool for the system integration. Here in the image also you can see that here is one electric vehicles, and these are the components are there, like the batteries are there, inverter, motors are there. So all the applications we are combined at one place, and then we can do the simulation of system. Now motor NVH. Now NVH is the noise, vibration and harshness. Due to the NVH, we have to do the simulation of NVH. Why we have to do the simulation of NVH? Because whenever we feel noise, okay, so that the efficiency drop is there. Sometimes due to the noise is there, the more harshness you feel, the more due to the vibrations, the more noise you feel. Okay, so for that we have to meet the noise standards, because the government use the law for this NVH calculations for the like the noise recognition. So for that you have to give the you have to meet that standards, whatever the standards you have, that your product is meet those standards to enter that product in the market. Now how Motor-CAD does the NVH approach? Like first in Motor-CAD what we can do, we have to supply the electric power to our motor. Okay, so first we have to do the electromagnetic calculation. So electromagnetic calculations is done by the Motor-CAD using the current driven approach. Okay, so it is using the finite element analysis method, which is based on the mechanical finite element method, which is do the calculation of like the how the causing torque is there, how the torque ripple is going to be there. Okay, it also calculates the how the stator and your rotor is interacting, means how the field values are interacting. So on the basis of that field values in the air gap region, so that in the air gap region whatever the field values are there, if something is missing in that field value, it causes that sound, sound like you can see in the motor, you can hear it in the motor. So because that sound is because of the air gap force. Then it uses the Maxwell stress tensor method, which is defined by the Maxwell equations to calculate the electromagnetic parameters. And then we have to see how the Fourier analysis is also there to calculate the natural frequency on the different modes. Okay, so after the electromagnetic performance, if we are checking all these electromagnetic performance, then we have to do the mechanical system. So we have to transfer this electromagnetic data into the mechanical system to see how this and these mechanical systems inside the Motor-CAD which governs the equation of the mechanical equation. So the equations related to the noise, vibration and harshness all are included in the background of the mechanical system of Motor-CAD, and in that system you have to see the how it is shot, and then you can see the how the response are coming, how the motor response are coming on the noise and vibrations. Then after the vibrations, the acoustic environment also there, you can see the patterns are there, how the sound power levels are there on the basis of different speed. Sometimes the different areas are there that you have to apply, like on the different speed region. Sometimes what happen at the medium speed region, like at the 6000 or 7000 rpm, your sound power levels are good, but at the higher rpm, like when you are going to the 12000 or 13000 rpm, so that time your sound power levels are very bad. So you have to apply the various conditions to the motor, like you have to change the geometry or change the shape of poles, or say like sometimes you have to use the skew method to reduce that power levels. Okay, so reduce the power levels means reduce the sound level obviously. And this noise is, all the noise is due to the stator radial forces in the motor. Now here you can see the patterns are there, how the radial forces are applying on the stator part. It uses the Maxwell, here the transient force acting on the stator, how the transient force is looking like. These are the radial forces value, transient radial forces you can see. Here the transient force is there, the transient radial force you can see here. Okay, and after these forces you can do the FFT transfer, like to know how the due to the torque or the due to the radial forces, how the Fourier transform look like, how the frequencies looks like, at which frequency, at which mode, like which space order is there, which harmonics are there. So all these you can see. And here you can see here, these are the space factors are there. Here the space order is there and the frequency. So what is the space order and frequency? The frequency is the time dependent, like it is based on your time, and then the space is like the shapes, how the vibration shapes looks like. Okay, so that here all these are the space orders are there. You can see the space 8, this is the space order 8, space order 16, and this is time order which is based on the frequency, and this is the shape you can see, like the force. These are the force component, the radial force component of the motors are there that you can see here. Now we will see the structural response, how the structural response will give by the Motor-CAD. It calculates the stiffness and the natural frequency for the each mode. Like here it includes the 4 modes are there, 0, 2, 4 and 8, and each mode you can see here the different modes are there. And in the image you can see, this is the image, the space order in the vertical y-axis, the space order is there, horizontal axis the frequency is there, and these are the sound power levels are there, you can see. Okay, so here here is the 95 picowatt is there. So here is sometimes around the space order here at 0 and at around 7000 rpm. So that in this way you have to analyze and you have to conclude the motor, like at which sections, like at which speed my motor is getting more noise. So that you have to check inside the Motor-CAD the structural response also, and it will give you the indication that at which mode your rotor becomes more stiff or stator becomes more stiff. That indication is also give. And these are the acoustic response, you can say the same power, the speed, these are the power levels, and you can see this the harmonics are there. And this is the spectrogram which gives you the same results are there. You have to just read out the results, whatever the results are there. Like here you can see the more sound levels are there. Okay, more sound powers are there in the specific, like at 6000 rpm. Okay, so to reduce that whether you have to use the skew method. The skew method is also there. You have to use the skew method, or you have to change or change the shape of the any of the parts, like the magnet shape you can change, the poles or tooth shape you can change of your motor, and then you can see the change in our natural frequency and the power levels also. So if your power levels is less, if your frequency is less, then your sound means your noise is also less that time. Now in ANSYS, Motor-CAD is one of the tool which has the capability to do the electromagnetic, thermal, okay, the lab simulation as well as the NVH simulation. So inside the Motor-CAD, for the when you are starting from the scratch the motor calculation, so that time from the concept, for the concept design, the Motor-CAD is the best tool for doing the multiphysics analysis. Okay, but whenever you are going in advanced level, okay, to go in the high fidelity analysis, so for the high fidelity analysis we have the different tools. We have to combine the different tools which has some specialization of each tool. Like the Maxwell is specialized in the electromagnetic simulations, okay. The mechanical tools are there which are specialized in the structural analysis, the harmonics, the noise analysis, and some of the sound tools also there, like the ANSYS sound is there. Okay, so ANSYS sound is terrific in predicting the noise, how the noise is there, what is the noise units is there, like the how many decibels noise are there, so that predicting the ounce this ANSYS sound. So here first I have to do the magnetic simulation, then I have to see how the stator excitations are there, how the we have to calculate simply the forces value, the radial forces value, and then we have to do the dynamic behavior with the acoustic radiation, then we have to transfer those paths, and then you have to see the how the sound actually perceive. Okay, so this is basically the intro of the NVH calculations. Now we are moving to the hands-on sessions which we are doing on the ANSYS Motor-CAD. So first here I'm searching for ANSYS Motor-CAD, this one. Okay, this is the ANSYS Motor-CAD tool is there. Here the 25 R2 version is there. So as this 25 is running, so 25 R2 versions are there. At each year the two versions are there. And here we are designing one of the motor. So before designing one of the motor, I will show you what are the models are there inside the Motor-CAD. So in one models, here the four different models are there. Okay, the electromagnetic module is there, thermal model, lab, and mechanical model. So for the electromagnetic performance, we refer the electromagnetic E-magnetic module. Then for the thermal sections, we refer the thermal module, and for the drive cycle analysis or duty cycle analysis, we refer the lab module for the efficiency map calculations or torque speed curve calculations or the operating points calculations. Then for the structural response, to check the structural response or the vibrations or the simply the NVH calculations. So electric NVH calculations we can do in the ANSYS mechanical. And these are the supported motors are there. Here you can see the motor types like the BPM motor, induction motor, SRM, BPM outer rotor configurations, PM DC. So these are the 8-9 types of motors are there. Here you don't need any geometry or anything, you just need your parameters, whatever the parameters that your motor has. You all need to just put your parameters like slot number, stator lamination there, all the parameters you need to get there. Okay, and then you can see the motor, give the materials data, whatever the materials data that your motor has, and then you have to do the calculation. So like here we are in the mechanical section. So first we go in the electromagnetic, and then we will see the all these parameters. So first I would open one of the open template model. So from the file open template, so I will open this one model, e-mobility model, the automotive NVH models we can open now here. This one, just open template. Okay, I'll just save this model once. Okay, this machine is the 48 slots are there and the 8 pole machine is there. Here you can see the 48 slots are there. Here these are the slots are there which are indicated in the yellow section, and the poles are there which is 8 poles motor is there. Okay, and this is the winding pattern is there. In the geometry you can see this is the axial view, this one is the axial view, this one is the radial view, and this is the 3D view. Okay, so you can see the 3D view also of the motor. Then after the geometry sections, then we have a winding section is there. So in the winding you have to give the winding parameters, whatever the winding parameters you have, like which type of coil style is there, hairpin or the stranded winding is there. Okay, so you have to give that. You have to give the windage definition, like the wire size is there or the copper slot fill factor is there. Then after that you have to give the pattern, like which type of winding pattern you have. You have to give the number of phases, throw means the coil pitch is there, winding layers, the parallel paths are there, and then you have to see those values, like how the mmfs are there, how the harmonics looks like, how the mmf diagram you can show for the each phase. Okay, and then you have to see the phasors, means at how each phase is apart from each phase, like here the 120-degree phase difference is there. Okay, so after the winding sections, then you have a input data. In the input data, the properties like materials properties are there. Along with that material properties, whatever the materials have for this motor, like for the stator laminations, the NO181160, this is the material. So how much the weight of that material is there? Here also the Motor-CAD give you the weight value, like 13.28 is the weight. Like for the armature the weight is there. Now for the total weight of your electric machine is 34.36. So this is weight is calculated on the basis of the density is there. If your density is wrong, then your weight calculation is also wrong here. So you have to give the appropriate density value here. Okay, so if you have the density value, if you have the correct density value, then you can give the accurate density value here, and on the basis of the density value it will software automatically calculate the weight parameters. So here after the input data, the calculations tab is there. So in the calculations we have to give the, like for the motor we have to give the at which RPM my motor is working. So right now it is 5800 RPM, current line definition, RMS or peak. Okay, so we have to select some parameters like winding connection, the star or delta is there. Okay, then the coupling is there. If you want to couple electromagnetic and thermal, so coupled means you have to simply transfer your losses. So whatever the losses you have in electromagnetic, so transfer these losses can be transferred into the thermal sections, and then in the thermal sections along with that electromagnetic, in thermal section you can see the temperature data or the heat transfer data. Whatever the heat transfer data is there, how the heat flux values is there, how the heat transfer coefficients are there for the natural convection or forced convection. So you can see those all thermal parameters inside the, and after the coupling method, the skew method is there. So skew method is very important when you are doing the, like the torque ripple calculations or the NVH calculation. So because of the torque ripple also the noise is getting generated. Okay, so to see or to do that calculations in 2-3 minutes, we will use this skew method to reduce the noise. First we will see the without skew, and then we will see the by using the skew. Okay, now the on-load parameters. So I just calculate the magnetic parameters, the electromagnetic parameters of this motor, and now we will see these parameters in the output data, like which parameters it gives, the which output values it gives all the electromagnetic value, like your efficiency, average torque value, the inductance value, the flux linkages value, all the value it will give. Just wait for a moment. Once the calculation is done, we will see the results. Okay, okay, now the calculation is done now. So we'll just go to here and see the output data. Like here the electromagnetic data is there, here the drives data. In the drives, like line to line supply voltage or the DC bus voltage. Here in electromagnetic you can see the torque, how the torque ripple values are there, the percentage of torque ripple, the electromagnetic power, output power, total losses. So all these properties you can share, like the shaft torque value is how much the torque the machine is generating. The shaft torque is around 498 Newton meter. Also the power factor, all then the phasor diagram, equivalent flux density and the losses. So these all winding parameters you can see here, all the parameters regarding the electromagnetic. And then the graphs is also there, the terminal voltages graph, the torque graph, the air gap flux density graph. So all the parameters you can, all the electromagnetic parameters you can see by using this electromagnetic. Okay, so now we are focusing on the NVH part mostly. So what we are doing now for the NVH, to calculations, and in the calculations first we are doing the calculations by using the none, and then we are using the skew option. And if you are using the skew, then rotor slices the angle is automatically created by the software. Okay, first we will use none, and then we are using the rotor, and we compare the value of the, like we are comparing the results of the NVH. None. Now go to change the model to mechanical. Okay, now in mechanical also the same things are there. Whenever comes in the mechanical section, okay, now the mechanical section is there because it is showing the stress here. Okay, the one parameter is added, housing is added there. Now here in Motor-CAD you have the option to add the multiple ducts also at the rotor rod. stator parts. Here the stator ducts, none rotor ducts. If you want to add the ducts value, then you can add. Now you can see here the path also. Here the fluid flowing path is there. Go to calculation. Okay, and here the rotor stress is there. Rotor stress, shaft speed 500. First we will calculate the stress value. Do not include magnets. And here it will give like the stress value is there. So it is a simple calculations that you are doing the Motor-CAD. Like here in the stress value at these positions you can see it is around the, it means the maximum value of the stress is 24.5 megapascal. So right now the magnets are not there. So if you are adding the magnets, then what is happens? Include magnets now. Just calculate the rotor stress parameter. Here the magnets that you can see here. Now the stress parameter is almost doubled. Okay, so which is 52.38. So it is concluded like when you are adding the magnets here, magnet is also responsible to add the some stress value at the rotor. Okay, so to check that stress value, now the stress value on the rotor part which is 52. Now we can see what is the strength is there. Okay, the maximum strength of that rotor part. So the maximum strength of rotor part is here yield stress. So yield stress is the value that this rotor part can sustain. Okay, so right now it is 445, means 55 it is easily sustainable. Okay, now for the electric vehicle the NVH calculations and the forces calculations. Here when you are coming in the NVH section, the torque and the, here we have to give some load points are there. Okay, you have to add the load points also. Here already created the load points. If you want to add, then you can just click on this add buttons and then you can add the torque like the load points. Load points means you have to give the load points on the basis of the torque and your speed value. Here the 5 load points are there. Requested torque and the speed value you have to give, and it is calculated the torque, peak line current and the phase advance. If you have the current and phase values, then you can give those values also. On the basis of that value, that requested torque and the speed values will be calculated. First I will off this torque envelope, and here this is the one operating point here. Okay, this one is the 258 rpm, and then it is at the base, at the baseline rpm which is around 5800. Here our base rpm is there, so at which rpm we calculated the electromagnetic performance parameters, and these are the some other points are the torque and current points also there. Okay, so now first, before moving for to generate the NVH and the forces values, so first you would inputs, settings and calculations, and we will increase this torque calculation points here. Okay, so it is like the transient points you can say. So instead of 45 I will give the 90 value. Okay, and just move to the calculation, generate ENVH of this one, generate ENVH and forces. Now it will calculate the NVH value and the forces value. Forces means here the force is there, only radial force is there. Okay, so it will calculate those radial forces value, and on the basis of that radial force we will see the results, how the natural frequencies graphs looks like, how the modes are there, and how the shapes of that mode looks like. So on the basis of mode and the different space order, how the natural frequencies will be varied. Now in the meantime, if you have any questions, then you can ask also. So right now it will take 1 or 2 minutes to solve it completely. In the meantime, you can ask any questions if you have, or you can put your question in the chat box also. Okay, now the force calculation is completed here. And now you can see the requested torque values. I will go to the ANVH sections. Okay, ANVH, and these are the torque results you can see on the basis of the different operating points. Okay, now first we will select the baseline RPM, which is 5850, and you can see the torque values is there. Means you can see here the torque ripple values basically. Okay, and this is the harmonic amplitude, and these are the harmonics angles are there. Okay, the torque angles you can say. At different the baseline also you can see, and at the mode the stiffness is there. How the modes here you can see the modes are there. Okay, the 25 modes are there. Modes is nothing but the vibration patterns are there. Okay, so at each mode the stator is excited by differently. Okay, so on the basis of that the natural frequency is getting calculated. So you can see the natural frequency graph is also there. Just go to acoustic spectrogram. Now you can see this is the spectrogram is there. Okay, so in the horizontal axis the sound frequency is there. Okay, and in the vertical axis speed is there, and on the right hand side you can see this legend window is there. So this is the sound power is there. Okay, the radiated power is there here, which is in the pico. Okay, now you can see at which part the sound power is more. When the sound power is more, that time your sound is also more, means your noise is more that time. So you can see that this sixth harmonics here, when I see the sixth harmonics and the RPM is around 14,000. Okay, and the sound frequency at that time which is around 5674 hertz at sixth, and then at the 12th harmonics also here at the 12th harmonic. Whenever you are seeing here the red color is there. Okay, so now in the 12th harmonics you can see in the middle around 7000 RPM the sound power is more, and after the 7000, or you can say between the 6 and 8000 the sound power is more, and after that the sound power is getting reduced. Means at that time what happen, the radial forces also getting decreases that time at this peak RPM, like at this 7000 RPM the radial forces are more, and because of that radial forces the frequency is more, and if the frequency is more then motor generate the more noise, and if the motor noise is more then it will show you the value of that sound power is more here at this particular 7000 RPM, or you can see the 8000 RPM is there. Then you can see the forces here, the forces value is also there on the basis of time and harmonic amplitude. Here the harmonic amplitude and the force value. These are the space harmonics. You can see the frequency domain 2D. Okay, here the same thing is there. now you can see here. Okay, so if you want to see clearly, then now we want to see this frequency domain 2D graph clearly. So just domain calculations. Okay, go to calculations of the electric NVH, and then you can see the. So here you can see this red part is there. Okay, so this red part is basically meaning here the force 31.79 decibel, and the space order is 8 and the time order is 2 here. Okay, at the same time here space order and time order you can see for the each component. Okay, you can just see like this, just touch, and here you can see the space order and like the force value as well as the space order and the time order. Okay, like in the Campbell diagram show the spectrogram for the different modes. Mode 8 the different spectrogram is there, and for the mode 8 you can see here this one at which harmonics, like the space order 8 and time order 2 here. And now you can see the frequency pattern, like at which RPM you want to see, like this base RPM if you want to see, then just go and here click on just generate animations. It will show you the animation. Okay, means it is the excitations on which is apply on the like the radial forces, how the radial forces are applying the excitation on the stator part. Like you can see this on the 6th order also, like on the 10th order, 12th, that like the 12th order. Okay, now you can see the patterns are there, the second also. Okay, these are the orders you can see, like this is for the second order, 6th order and the 12th order. So here you can see for the different operating points also, like this operating points you can generate the same animation. Now you can see the animation. So these are the patterns are there, or these are the radial forces, how the radial forces will be acting on the stator part. The torque values are there, the forces is also there. Okay, now you can see the time harmonics also here, how the time harmonics is changing and its amplitude, how much the amplitude is getting change here. Go to acoustic, and here the order tracking, and you can see the graph here. Okay, the frequency versus space graph here, the power, okay, and this is the speed, and this will give you the like time and the space order. Okay, so here at the higher speed, at this point the power is more. Okay, you can see the power is more, means at this point the sound is also there. Here you can see the power is around 17, yeah, 96.1786. Okay, so this much the sound power is there, so means the noise is more at this region and the frequency is also more in this region. And you can see the some distribution of this power and the power versus speed. So at this speed the sound is also the frequency the in the medium section, it is not like the very low, but in the medium section the frequency is there, and here indicates the space order and the time. And also in Motor-CAD you can see the sound also, like generate and play sound. At 94 decibel sound is there. Here on the basis of the calculations it will give you the like the how the. Okay, okay sir. Now here these are the, where is that graph? Here this is the graph for the non-skew method. Okay, so now we will just see the same graph for the other calculations, means for the skew calculations, and then we can see how the difference is there in these two graphs. Okay, this one is the first graph is there for the skew one. So upon the same geometry, and now we will do the calculation for the skew method, and then we will compare the results then. Go and open the same template, D10. Go to calculation, A magnetic. Here skew. Just go to mechanical. You can do the analysis here. Calculate again. Now it is calculation for the skew. When you are skewing our rotor, how the operating points are there, and on the basis of the operating points, how the results are coming. That we will see. In the meantime, I will give the answer of the questions also. What the sir is asking. As the higher order harmonics we can't consider as its higher order. We can consider for image calculations like 12. So in practical applications, so higher order we can consider beyond the 16th. Okay, so like up to the 16th order we cannot consider the 16th is the higher order. Okay, so beyond 16th we can consider the higher order in the practical applications. As we are talking about the practicals, so beyond the 16th or 18th we consider that as a higher order harmonics.
If anybody has any question, you can please write it in chat box.
Or you can unmute yourself and ask me the questions, whatever the questions that you have regarding this webinar, like regarding in the NVH parameters.
Hello, sir. This is Bhagwat.
Yes.
Sir, in this simulation, are you considering inverter harmonics also during the NVH?
Yes, sir, yes.
No. My question is this, sir. As in this motor-CAD, whenever you by default drive sections are there, this is considered the inverter harmonics also.
Yeah, sir, it considers the rotor harmonics also.
not a rotor harmonics, sir. I'm asking for inverter harmonics.
Yeah. Inverter harmonics. So that inverter harmonics we can, no, this is for the motor. The motor CAD is only considered the motor harmonics.
Okay,
So
sir.
for the inverter harmonics, you have to do the electric motor. Okay. So for the inverter harmonics, what you have to do? You have to do the simulation in the ANSYS Twin Builder. Okay, here you can consider your electric motor as well as the inverter harmonics. So here you can simulate those inverter, and on the basis of that inverter values, you can see the harmonics there in the ANSYS Twin Builder, not in the ANSYS Motor-CAD. If you want both the harmonics, then you
Okay.
have to couple ANSYS Maxwell with the ANSYS Twin Builder. So you will get those both values, okay, on the harmonics.
Okay, sir.
And
Thank you.
the one question is there which you correlate the simulation results. Okay, means you require the experimental results. So after performing the simulations, what you can do, if you make any optimized designs, then you can do the experimental simulations, and after the experimental simulations you can compare these values. Okay, like the experimental values and this simulation results values, whatever the results values you have, you can compare this. So in these sections you can compare also. Here adjust model results, and here you have to just add the results, and you can just adjust those results. Okay, you can adjust those model results also. But to compare the results, you require the both the like the simulation data as well and the experimental data as well to compare those values. After that process also, after that process you can go for the in the manufacturer. From others, any questions? So in the meantime, all please are fill the feedback form also. So you will get the webinar certificate also from the ANSYS. Okay, with the collaboration of ANSYS and ARK, you will get the participant certificates for this webinar.
Yeah, requesting everybody to please fill the feedback form so that we can provide you the certificate. And after this, Monday, we will be uploading this session video on our YouTube. I have shared the link, requesting all to please like and subscribe our YouTube channel too.
Yeah, you can go. Here in this you have to give the input value, whatever the input current values you have, you have to give those values here in the electromagnetic section. You can see the graph here. Okay. Here you can see the result, this one. Okay, now this rotor, now you can see the result. This is the skew one. Okay, and here you can see most of the harmonics are there in the sound level around here near 40. Okay, so at the average you can see the 50, around 50. Now here when you are giving the skew model, now in the skew model you can reduce the harmonics here. So the harmonics is around now around 40 is there. Okay, now for here the harmonics is there. For the high speed, the high speed the harmonics is almost same, around 95 is there. Okay, so by using the skew model, or you can change the shape also, the shape of the stator and the poles or the teeth shape. You can, by reshaping those constraints, you can just plot the results of the harmonics, and then you can see the results also. Like in this way you have to do the NVH analysis by trial and error method. You have to change the multiple parameters, and on the basis of those multiple parameters you will get those results. Okay, now for the skew you can see this results one, this one tab. So this motor design, the motor NVH is for the concept design. It is not, you can say it is not like the high fidelity analysis. Okay, so for the high fidelity NVH calculations we have a different tools. Now please feel free to ask the questions, whatever the questions you have. Any maximum number of mode shapes we can visualize. Here in motor around 24 is there. In my opinion around 24 is there. More than 18 is there. Okay. The resonance noise other than the skew. Other than the skew you can, by changing the shape of your geometry, the geometry optimizations you can say. Can use the geometry optimizations method, like to change some parameters in the geometry, or change some curves like between the, because of this noise is generated mostly because of this air gap flux. Okay, so to cancel out those air gap flux we use the skew method now, but sometimes what happen, by using the skew methods also that air gap flux is not cancelled. Okay, so to cancel those air gap flux values and to cancel those radial forces we have to use the geometry modification method, like to adjust the some curves in your geometry, so it can get the more clear idea about the that radial forces to cancel out. If the radial forces are cancelled out, those air gap flux distribution, or you can say the air gap field is getting cancelled out, then there is no noise is there. But in practical it is not possible to complete no noise application. Okay, the some noise is there, but you have to cancel out maximum of their components. Based on which parameter to decide the NVH results are good. Okay, you can see this graph is there. Okay, the mostly the frequency is there, the harmonics. Okay, harmonics, the space order and the time order is there. Okay, and then you can consider the sound power. Okay, basically the all the results are depending on the sound power. Producing circular notch in the stator. You have to try this one. I am not orally saying this like it is reduce the noise or not, because it is depend on the number of poles and whatever the number of teeth that you have in your geometry. It is based on that one. Now anyone have any question? To decide the sound power level, standard value I don't know actually what is the standard value, which is in my opinion it is based on the applications, like which applications that you are using. Okay, others also, if you have any questions you can ask. Yeah, this method is also sufficient. Like in the for due to the switching circuit also the noise is getting generated. So if you fix those switching or the inverter switching method, then you can reduce the noise also. But you have to connect that like the electric motor and the inverter, you have to connect that one. So for that you have to use the ANSYS twin builder. So this is one the complete the one platform where you can couple the different tools of ANSYS. Okay, so Motor-CAD is like the separate tool, Maxwell is like a separate tool is there. So if you want to couple both the tools like Maxwell and your inverter circuit, so you have to use the twin builder. In twin builder itself you can create your inverter circuit, or if you have already created inverter circuit, then you can just transfer your inverter circuit in the ANSYS twin builder, and you have to transfer the Maxwell or the Motor-CAD design in the twin builder also. Then you have to couple, and then you can see the results values, and then you can like here you can see is the noise level is getting reduced or not, that you have to compare there. Aerospace generator or aerospace motor, okay, that you have to check whether it is available. We will share with you on the email. Okay, so if the case study is available, we will share with you. From 3 to 6, does this have any impact on? We are talking about from 3 phase to 6 phase. Okay, so you have to check at each phase, like if that you have to check in the software itself.